Venus. First studied closely by NASA's Mariner 2 in 1962, Venus sits only 41 million kilometers from Earth, yet remains one of the most hostile worlds in the solar system. Its thick carbon dioxide atmosphere drives a runaway greenhouse effect, producing surface temperatures near 465 degrees Celsius, hotter than Mercury despite being farther from the Sun. The atmospheric pressure is 92 times stronger than Earth's, equivalent to being nearly a kilometer underwater, crushing unprotected equipment in minutes. Clouds of sulfuric acid blanket the skies, making the planet corrosive as well as scorching, while winds in the upper atmosphere reach over 300 kilometers per hour. The severe conditions of Venus, confirmed by Soviet Venera landers that survived only minutes on the surface, highlight why even the closest planets can be places no human should ever visit. Triton, Neptune's largest moon, was discovered in 1846, just weeks after Neptune itself, and studied up close by Voyager 2 in 1989. It orbits Neptune in a retrograde path, moving opposite the planet's rotation, which indicates it was likely captured from the Kuiper Belt. Surface temperatures average minus 235 degrees Celsius, making it one of the coldest places in the solar system, and its thin nitrogen atmosphere cannot sustain life or protect against radiation. Voyager 2 observed geysers of nitrogen gas erupting several kilometers high, driven by seasonal heating beneath its icy crust. Because its orbit is unstable, Triton will eventually spiral inward and be torn apart by Neptune's gravity, forming a temporary ring system, marking it as a world both hostile now and doomed in the future. Neutron stars. Formed after the collapse of massive stars in supernova explosions, neutron stars compress about twice the mass of the Sun into a sphere only 20 kilometers wide. Their density is so extreme that a sugar cube-sized piece would weigh over 1 billion tons under Earth's gravity. In 1967, Jocelyn Bell Burnell, then a graduate student at Cambridge, first detected their presence by recording the rapid pulses of radio waves now known as pulsars. Many spin hundreds of times per second, releasing beams of radiation so powerful they would strip any nearby planet of its atmosphere and sterilize its surface. The recognition of neutron stars laid the groundwork for studying even more dangerous relatives with stronger magnetic fields, magnetars. Magnetars. Among the rarest neutron stars are magnetars, first detected in 1979 when satellites recorded sudden, violent X-ray bursts from deep space. Their magnetic fields measure up to a quadrillion times stronger than Earth's, strong enough to wipe digital data from over 1,000 kilometers away. These fields can twist and fracture the star's rigid crust in events called starquakes, each releasing energy equivalent to 10 to the 15th nuclear bombs. NASA's Swift Observatory continues to monitor these outbursts, recording their unpredictable flares and helping researchers understand the instability of such exotic remnants. The study of magnetars naturally connects to the broader category of quasars, whose extreme radiation also marks them as places no traveler should approach. Quasars. First identified in 1963 when Martin Schmidt analyzed the spectrum of 3 C273, are powered by supermassive black holes devouring surrounding matter at extraordinary rates. The brightest of them, including 3 C273 located 2.4 billion light-years away, emit up to 1,000 times the total energy output of the Milky Way. Their intense radiation sterilizes any nearby planets instantly, flooding space with lethal jets of ultraviolet and X-ray energy. Despite their immense distance, some quasars are so luminous that small backyard telescopes on Earth can still detect them. The discovery of quasars highlighted the dangers of extreme radiation environments. Hypervelocity stars. First confirmed in 2005 using the Sloan Digital Sky Survey, hypervelocity stars are rare stellar objects ejected at speeds of millions of kilometers per hour. Their extreme velocity usually results from a gravitational slingshot effect near supermassive black holes, which can accelerate stars to escape velocities far beyond the Milky Way's pull. One such star, US 708, travels at 1,200 kilometers per second, fast enough to leave the galaxy entirely. Any planet bound to a hypervelocity star would be stripped of its atmosphere almost immediately due to intense radiation and tidal forces. Cosmic rays. First detected in 1912 when Victor Hess carried electroscopes on balloon flights, are high-energy particles that travel through space at nearly the speed of light. The most energetic events exceed 10 to the 20 electron volts, making them billions of times more powerful than particles accelerated in Earth's largest colliders. These rays constantly bombard our planet, but Earth's magnetic field and atmosphere deflect or absorb most of them before they reach the surface. For astronauts and satellites outside this protection, however, exposure can damage DNA, disrupt electronics, and degrade spacecraft materials. The unsolved challenge of shielding against cosmic rays remains a major obstacle for long-duration Mars missions, connecting directly to other unexplained large-scale cosmic motions like dark flow. Dark flow. In 2008, researchers analyzing data from NASA's Wilkinson Microwave Anisotropy Probe, WMAP, identified an unusual large-scale motion now known as dark flow. They measured hundreds of galaxy clusters moving at roughly 1,000 kilometers per second in a common direction that extends beyond the observable universe. This persistent drift defies predictions of the standard cosmological model, which expects random motion on such large scales. Some scientists suggest the pull may originate from massive structures outside our cosmic horizon, while others cautiously propose interactions with regions belonging to different universes. Because the cause remains unresolved, astronomers still classify dark flow as a cosmic mystery. Rogue planets. Astronomers first identified candidates for rogue planets in the early 2000s, estimating that billions may drift through the Milky Way without parent stars. These worlds wander in darkness, cut off from stellar energy, leaving their atmospheres to collapse into frozen, inhospitable states. While some models suggest subsurface oceans could persist beneath thick ice layers due to residual geothermal heat, no direct evidence confirms such habitats. For humans, the absence of sunlight and external energy sources makes colonization virtually impossible, as survival would depend entirely on artificial power. The recognition of rogue planets concludes the catalog of cosmic places too hostile for life, emphasizing how extremes, whether blinding radiation, crushing gravity, or endless cold, define the most dangerous corners of the universe. Europa. Discovered by Galileo Galilei in 1610 and revisited in detail by NASA's Galileo orbiter between 1995 and 2003, Europa is one of Jupiter's 4 largest moons. Its surface is a shell of water ice tens of kilometers thick, beneath which evidence strongly suggests a global liquid ocean containing twice the volume of all Earth's oceans combined. Despite this potential, surface conditions are deadly. Temperatures average minus 160 degrees Celsius, and Jupiter's powerful magnetic field bathes Europa in radiation strong enough to kill an unprotected human in a single day. Cracks and ridges stretch across the ice, constantly reshaped by tidal forces from Jupiter's immense gravity. The promise of an ocean below makes Europa a key target for exploration, but its surface remains one of the most uninhabitable places in the solar system. Jupiter, first observed through a telescope by Galileo in 1610, is the largest planet in the solar system, with a mass 318 times that of Earth. It lacks a solid surface, instead transitioning from crushing atmospheric layers into a deep ocean of liquid hydrogen, where pressures exceed millions of atmospheres. Winds in the upper atmosphere reach 600 kilometers per hour, while storms like the Great Red Spot have raged for at least 350 years. Temperatures and pressures increase so dramatically with depth that any spacecraft attempting to descend would be destroyed long before reaching the core. The impossibility of surviving inside Jupiter underscores why even giant planets within our solar system remain among the most unlivable places in space. If you enjoyed this, I'm going to be posting a lot here. I would greatly appreciate it if you could subscribe. Thanks for watching.